Okay, good afternoon, everybody. Chris here from RF Venue, here to introduce Don Boomer, who is going to be taking us through the webinar this afternoon, talking about coax cables. Don, please go ahead and take it away. And folks, feel free to post your questions. We'll have a little Q&A session afterwards. And
Okay.
just to reiterate, the recordings for the webinars will be up on the blog. We still need to post the one from last week, but we'll get that up tomorrow. So be sure to check out rfvenue.com/blog for the full series of recordings. Don?
So today we're going to discuss the exciting and glamorous world of coax cables. You know, I think we kind of treat this as the redheaded stepchild, but actually coax cables are very important to making your system work. So what is a coax cable? Well, there you go. There's a coax cable. What makes this a coaxial cable is the symmetry from that center core to the braided shield. So this is what a typical coax cable looks like when you cut it in half. I'm sure you've all seen this. The signal runs down that center core, and then there's a dielectric, an insulator, and a shield around the outside of that, and then a plastic jacket. What makes this cable work is the fact that that center core is precisely centered in the middle of that braided shield, and that the whole cable is round. If it becomes unround, then bad things start happening. So this is a typical coax cable. This is a better coax cable. And the difference between this cable and the previous one is in addition to the braided shield around the outside, there's also a foil shield. This gives it 100% shielding. Normally braided shield wires are up to 95% shielded. And you go, well, that's a 95%. That sounds pretty good. Well, yes, but that means that 5% of the energy going down that center core can escape out of the wire. It doesn't get to where it's going. And also it allows ingress of interference to penetrate that wire and get down inside, right? What happens with that foil shield is from that perfect center, the energy, while it's definitely going down the copper core, is also radiating out to the sides. And when it hits that foil shield, it bounces back down into the wire. So you're getting more efficient cable when you use 100% shielded coax cable. This is the cable that we most frequently use. It's called RG8X. Not all RG8Xs are the same. Ours is a truly 100% shielded cable, and you can see the cutaway there. Sorry, it's not very exciting, but that's how it works. And when you look at a spec sheet, every brand has their spec sheets. These are the parts that you really need to look at. For as far as wireless mic, I mean, you know, if you're an engineer, well, you can look a little deeper, but just to make our wireless mics work, this is what's the most important. So we want to see what the shielding is up on top, and you see it's 100% from the foil and 95 from the braid. Interestingly, about shields, the copper braids are good at shielding more low frequencies. They're going to shield out you know, AC cables passing close, low frequency noise. The foil shields are better at rejecting super high frequencies. So when you have both, you get the best of both worlds. Anyway, moving on. You want to check the impedance. For wireless microphones, almost universally, we use 50 ohm. I can't think of anything that doesn't. There might be something out there in the world. We need to use 50 ohm cables. And we'll talk about that a little more. And then you want to look at the attenuation. You want to look at how much loss there is. And this usually has a frequency, and then it talks about loss per over distance. So depending on what frequency your wireless mic is going to operate, you can see how much loss you're going to have. It's pretty clear from this chart that higher frequencies lose power much more quickly in the cable than lower frequencies. So in this case, we have a rating at 400 megahertz. We have a rating at 700 megahertz. If you're in the United States and you're going to run in the 500s, you're going to have to kind of split that difference. it's not critical, but I mean, you can clearly understand that, you know, it's going to be around 7 point something in the 500s. So here's something I get asked all the time: 75 ohm cable versus 50 ohm cable. I just want to point out, kind of before we dive into this, if you notice on the left, we have 75 ohm BNC connectors, and on the right, we have 50 ohm BNC connectors. Take a look at where the pin is in the insulators. You'll notice they are different. So you want to look at your cables. You just grab a spare coax cable. 75 ohm is most frequently used for video, for television. 50 is pretty much used for data for our wireless mics. But there's definitely a difference, and there's a difference in the connectors. So just thought I'd point this out to you. You can double check and see what you've got, but there's definitely a difference in the connectors, although you have to kind of look close. Okay, so why 50 ohm? Well, back in, I don't know, 1929, Bell Labs did a bunch of tests on cable for wireless transmission. And what they discovered was that the lowest loss cable was up around 75 ohms. They also discovered that the cable that would pass the most amount of power was down about 30 ohm. So you got a choice: low loss versus power. 50 splits the difference, right? So we end up with a cable that has good attenuation properties and good power handling properties. And I mean, if you're as old as I am, and you remember using this kind of cable to hook up your TV antenna, obviously there's other cables as well. This is 300 ohm twin lead, there's 450. There's a bunch of stuff out there in the world. There's some stuff that NASA uses that's 125 for, I don't know what they use it for, but I guess it gets you to the moon and back anyway. So there are many different kind of cables, but we stick with 50 because that's what everything is designed for in our wireless microphone world. So how do you know if you've got a good cable or not? Well, if you go on YouTube, there's 27 videos how to test your coax cable with a multimeter. But look closely, and you'll see that what they're testing it for is continuity or resistance. That's fine. It'll tell you that you have a 100% broken cable, but it won't tell you the quality of that cable where you're going to use it up in the 500 megahertz range or wherever you're using it. It can't do that. I'm gonna, because I'm away from the lab, I'm gonna use a little video that we've used in the past, and we're gonna show you a little bit about how to measure it.
Here we're looking at 25 feet of cable that we know from a previous quality control inspection is bad. A common way of diagnosing cable problems is to use a multimeter to check if there's a short within the cable's length. We've set this multimeter to function as an ohm meter and measure resistance. The meter audibly signals that electricity is passing through the cable as it should, even though we discovered during more advanced quality control measurements previously that it was bad. Multimeters are good for ballpark measurements, but they can still sometimes miss. For the full picture, we need more specialized tools, either a cable analyzer or a spectrum analyzer, like this Agilent. Here we're measuring a small length of reference cable to calibrate the system. You can see the instrument reads a perfectly straight line plotted across the top of the graph, indicating almost no attenuation. Now we hook up a 25-foot length of good cable to the analyzer. Since this cable is longer, much more attenuation is present, especially in the higher frequencies. Now here's the bad cable we examined earlier with the multimeter. It shows severe signal loss in the UHF band, even though it passed both a visual and electrical resistance inspection with a multimeter. This damage would manifest as significant drop in gain. We don't want to convince you to purchase an expensive scientific spectrum analyzer, but we do want to convince you to pay just as much attention to the selection and care of your cables as you pay to your microphones and receivers. And to keep in mind that sometimes damage can't be seen with the naked eye.
So if you want to run right out and buy an Agilent, I think they're about $10,000 these days. You can get a VNA tester or something. They're all quite expensive. You're just not going to make it with a multimeter. It's only going to tell you that you have an open or shorted cable, but it's not going to tell you the performance of that cable. And you know, these cables degrade over time. So, you know, it's kind of important to know that you've got a quality cable. So when you buy, you know, an off-the-shelf, cheapy molded end, gee, I'm saving a bunch of money on these cables, they may be perfect or they may not. How would you know? You wouldn't. I mean, you're guessing. All the cables that we sell, we actually bench check every single cable to make sure that it's the quality that it's supposed to be before it goes out the door. So we know, because when you look at the cables, they'll look fine, but you have to measure them to see what's really going on. Here's the thing, you've probably seen this, and we're not going to dive into this very deep. VSWR, voltage standing wave. It's also called VISWAR by, you know, ham guys, or return loss, right? So what happens when you put a signal down this coax, if both ends, if the transmitting end and the receiving end are perfectly both 50 ohms and your cable is perfectly 50 ohms, then all the power that you're either sending from a transmitter to an antenna or receiving from an antenna and shoving back into your receiver would go where it's supposed to go. But that's not the case. So what happens is some of the power gets reflected back. And we're going to pull up another video here and take a listen to Alec for a second.
Return loss is the amount of RF power lost to reflection. That is to say, if you put a given amount of power at a given frequency into an antenna, how much of that power is actually radiated out into space, and how much of it is reflected back into the line. To measure return loss, I need to use our Agilent spectrum analyzer, which lets me evaluate the return loss on a standard 50 ohm load. Let me tell you what you're looking at. The analyzer is sweeping multiple frequencies across the UHF broadcast band between 470 and 698 megahertz. The return loss at each frequency is displayed compared to the 50 ohm load. The closer to 0 dB, the worse the return loss. The farther down the graph, the better. Let's measure the return loss on this white no-name dipole. So over here, this particular antenna in about the 500 megahertz range is giving poor return loss that's near 0 dB. But over here in the 600s, we're getting a better return loss. Now let's switch from this one to a generic whip antenna. As you can see, the return loss across all frequencies in this range is worse than the previous antenna, which isn't surprising. A whip is a monopole antenna, a simpler design than a dipole. Now let's measure a dipole we found on a receiver imported from Taiwan. It's actually marked with a frequency range, 624 to 694 megahertz. So we expected to have a good return loss in that range. Let's find out. Sure enough, it has a big spike right in the middle of that range. If you were using this antenna on a receiver that operated in the mid-600s, you'd be in good shape. In fact, if you were operating on the exact frequency of this spike, you might see an improvement in signal level of maybe 5 or 6 dB. Here's an antenna from a Line 6 XD75 2.4 gigahertz mic system. It has poor return loss between 470 and 698 megahertz, which is actually what we expect. If we zoom out and change the range to 470 megahertz to 3 gigahertz, we see a spike right on 2.4 gigahertz, where the antenna is designed to operate. Nice job, Line 6. So, there you go. 4 antennas, 4 very different return loss profiles. Since dipole quality can vary so much, if you lose one of the antennas off your system, don't just order a generic one off of eBay.
So this may be slightly confusing, right? Because return loss is a double negative. What you don't want return, you want not return. So you want return loss. So when you look at these, they go backwards from each other. But that's why it maybe look backwards when you look at it on the meter. Because again, remember, it's sort of a double negative thing. You want return loss. Return loss means the power is getting to where it's going. On the other hand, if you see this number written as VISWAR, then you want a small number. So what we're really shooting for in the real world is to try to get a number that looks like 10 dB of return loss. More is better, but it's not much better and it's very difficult to achieve. So if 90% of the power goes from the antenna into the receiver or from the transmitter into the antenna, and we only waste 10%, That's a good thing. One of the reasons that the return loss becomes less or the VisWAR becomes more is if that cable, that coax cable becomes unround, if it becomes oval shaped. So if you're laying it down on the floor and somebody steps on it, or it gets rolled over by a hand truck or a forklift or whatever reason, or it gets bent around a corner or something, right at that spot, the impedance of the cable changes, right? So I guess we have to talk about impedance just a little bit. So impedance is the relationship between the capacitance and the inductance per unit length of the wire, right? We're not talking about resistance. If it was resistance, that's something you could measure with an ohm meter. That resistance is a DC thing, and we're talking about AC. So impedance, what we're talking about is a transmission line impedance. It's not a resistance. What keeps that cable at 50 ohms is the distance from that center core to the shield in relationship to what they used for an insulator, right? Different kinds of plastics have different property. Actually, air would be the best, but a little difficult, right? So there actually are air coaxes where they have standoffs in there, and they have the lowest loss. Excuse me, they have the highest loss and the lowest VisWAR. There's just some interaction with the plastics that they use, and that's why it's not perfect. But anyway, so I wanted you to get an idea of what this is. If you look this up somewhere, like I said, we're not going to dive very deep into this. I mean, if you really want to know about this, there's lots of technical papers. We can get out the slide rules and the calculators, and there's lots of formulas and stuff. But really what we're trying to do, if you're not an engineer, what we're really trying to do is kind of get all those rules of thumb. Let's get it right. What we need here is a big thing. What we need here is a small thing. Let's understand those, and we'll be darn good to go. I mean, if we really need to, we can get out, calculators and figure out stuff down to decimal points. But in the real world, everything changes so much. Don't get stuck in the weeds over, a half a point for something, because it's going to change in 10 seconds anyway. Okay, so let's talk about damage to coax cables. Obviously, if it looks like this, you're in trouble. I've seen coax cables get slammed in the lid of a trunk when they get put away, and they'll put some little notches in it like this. If somebody stands on it in a high heel or cowboy boots, they're going to crush that cable a little bit. Or if you run over it with a hand truck, or you're just pulling it on the floor and it gets wrapped around something, they wear out. They do wear out. These cables, I have microphone cables that are 30 years old that are 99.9% as good as they were the day they were new. But with a coax cable, it's constantly wearing out. It's constantly losing quality. So it's a little like tires on your car. Every time you drive that car around the block, you wear a little more tread off. Not noticeable from day to day, but 50,000 miles later, you got bald tires. So it's the same way with coax cables. It depends how many times you roll them up or don't roll them up, how gentle you are. If people roll them up in a nice big roll instead of a tight roll and wind it tight around their elbow, not a good thing to do with any kind of cable, but especially with coax cables. We do need to be aware of damage and wear that happens on these cables over time. Another thing you need to be aware of is the bend radius. I think a good number is to take the diameter of your cable, multiply that by 20, and we'll call that the bend radius. That'll be nice and safe. Now, a lot of spec sheets will spec out this bend radius, and they may even tell you a number. It might be all the way down to like 10 times, but I'd like to be on the safe side. We don't want to bend these things in corners as they go around. We definitely don't want anything that looks like this. So for a small RG58, RG8X cable, 20 times radius is looking like 4.5, 5 inches. That's about what your bend radius should be to minimize wear and tear on your cables. If you're an installer, you definitely don't want tight angles as you exit out walls and go around corners and over baseboard and those kind of things. And another thing you definitely don't want to do is you definitely don't want to fix that coax cable down with Romex staples, right? Every little bend you put in that cable, you're causing an impedance shift right where that is. And you're going to get a bunch of reflections in that cable that are going to affect your return loss, right? Won't kill it, but we're losing quality all the time. And what we really have to do, especially now that wireless is becoming more and more difficult because there's less and less space and more competition for the space. You already know that if it's BitChA. We're trying to do everything smart. So these are smart things to do. You know, if you do it wrong, will it work? It might, but it'll work a whole lot better if you do it right. So that's kind of what we're trying to point out here. So here's some things that may not be obvious. Outdoors, especially. Sunshine. If you've got cable that is out on the side of a building or something, or it's even just, you know, laying on the ground, you're doing a festival, it's outdoors and your wires laying on the ground for a day or 2 days or something. Heat bothers these cables. Now, the insulator that's in the middle there, the dielectric that we showed, is usually polyethylene or PVC, that kind of thing. And that has a melt point of about 150 degrees Fahrenheit. So what can actually happen in these cables with a black jacket sitting out in the sun, they'll heat enough, especially when they're curved, when they're bent around something, that literally what starts to happen, this sounds crazy, but the center conductor starts moving a little bit inside that cable. That cable melts a little bit and it becomes off-centered and it starts to change your impedance. So not going to happen quickly. A lot of portable shows out in the sun, it's going to eventually wear out your cables. I get asked all the time, is your antenna waterproof? Well, that's a different subject. But if your coax cable is out in the sun all day long, years and years and years, it's degrading all the time. Second thing would be water. Coax cable does not like to be wet. And if there are any little cracks in your jacket on the outside or nicks or anything where water can penetrate that cable, it's going to seriously degrade its performance. So be aware of that. Obviously, I probably don't have to tell you, don't run your coax cable, underwater. Probably not a good idea. It's gonna screw it up. So just some other things to be aware of. Coax cables, it doesn't make any difference whether you're running digital wireless or analog wireless. In fact, almost nothing matters as far as antennas or cabling with analog or digital. You can run either or both at the same time. That's no problem. Think of it this way. It's like a telephone. You pick up a phone and you talk to somebody on the other end. It really doesn't care what language you speak in. It sends it down the wire. What you do with it at the other end, depends on who's on the other end. So if you're speaking English, the guy at the other end better understand English. If it's French or Spanish or Chinese, then he better understand that. But it goes down, it works over the phone. And it's the same way with your cables. So you don't have to worry. There are no digital cables specifically, at least at this point, because RF is RF. Analog or digital is the information. That's like the language you're speaking on the telephone, but the telephone works in either direction. Another thing I see in some places, in some owner's manuals and some seminars that I've seen, they'll tell you that coax cables need to be the same length. So if you're using a pair of paddle antennas and one antenna is 20 feet away and the other antenna is only 5 feet away, no, you don't have to put the same 25-foot coax on both sides and coil the other one up. You can use a shorter cable. Now, you'll get a different signal. You won't have quite as much loss, but frankly, that's not really something to worry about. I mean, if you get too much signal, you could overload, and if you get way too much loss, but the difference in reasonable lengths of coax isn't really going to make any difference because your signal level can easily vary 20 dB as the performer walks around the stage. It's going up, it's going down. So being exactly matched just isn't a thing. In fact, your antennas don't have to match. This might make sense. You have to always pick the right tool for the job. But it's perfectly possible that you may have a situation where you have a paddle antenna on A and a dipole antenna on B. That can make all kinds of sense if that's the right thing for your particular setup. So in any event, these things don't have to be the same. So here's kind of what I'd like you to take away from this. Again, non-engineering level, let's just talk about general best practices, rules of thumb. You want to use 50 ohm, a low loss coax. Now, can you use 75? Yes, it's lower loss, but it's more mismatched, so the return loss is worse, is more of a problem. And it's also possible that in a receiver, so if you've got an antenna that's going to a receiver, that receiver most likely has some kind of filtering on the input, and that filtering is most likely passive. And so the tuning of that filter depends on impedance. So if you stick 75 ohm coax instead of 50, you'll change the characteristics of that filter. Frequency to some place where you probably don't want it to be. So I would recommend that from this point forward, you use 100% shielded coax. It only costs 5 or 10% more. Cheapy, molded, no-name cables. You're playing with fire. I mean, they're just not going to work as good. You just spent $500 for a radio, and really saving $5 or $10 on a cable kind of seems like a bad bet to me, but there you go. You need to treat the coax cable carefully. You need to be kind of gentle with it, the way you roll it up when you coil it up. Obviously, over-under wrapping is a good thing to do, and it needs to be, make it at least a 1 foot circle. A 2 foot circle would be better. Again, it puts less stress on accidentally getting a kink or something in that cable. Frankly, if you get a hard kink in a cable, I'm tying a knot and that's going bye-bye. I'm not going to use that anymore. I can't lose the show over one bad cable because, somebody crushed it, even if it appears to work. What frequently happens is you set up a system before a show and it will be more critical. You just don't want any more problem than you have to have. And lastly, I would consider coax expendable, especially if you do portable shows, you roll them up. If you had a tester, you could test it, but every year, every 2 years, you just need to retire your cables and buy new ones, not 100% performing coax cable, right? I mean, they're going to drop down. It starts out at 99.9 when you buy it, and every time you use it, you're losing a little bit. How fast that is, can't tell you. It just depends on things. How much you can lose, I can't tell you that either. You could lose 1%, 2%, 5%, 20%, 50%. You could lose 50% and it might work fine in some instances, and in some instances you're off the air. So coax cable is a pretty small expenditure, I guess I would say, to go with your wireless system. So you want to use good cables. So that's sort of my exciting take on coax cables, and we can have some questions now, Chris.
Great. Thanks a lot, Don. Appreciate it. Couple of questions in terms of interfacing 50 ohm cable with 75 ohm cable, using a 75 ohm connector on a 50 ohm cable, that kind of thing. And there seems to be some sort of confusion around that.
Yeah. So, well, first of all, it is possible to use the wrong connectors on the right wire. So you can put 75 ohm BNCs on 50 ohm cable or the other way around. So, if you make your own cables, which is, kind of risky, you really have to be good at it. Not like making mic cables. You've got to be really good at making coax cables. But, if you went and bought a grab bag of BNC connectors and didn't pay that much attention to it, you're getting some mismatch on each one. Now, it is possible you can use 75 ohm cable, and you can buy specially made transformers for each end, but I mean, that's pretty expensive. There may be some particular reason to do it in some cases, but as a general rule, I would think that's not very cost effective. And like I said, in an emergency, if that's all you've got, will it work? Probably. It just won't work as well. You're losing in the mismatch, right? So if your transmitter is perfectly 50 ohm, and the cable's perfectly 50 ohm, and the receiver's perfectly 50 ohm. I guess I should have said antenna, but you get it. The path works either way. So it's the same thing for in-ear systems. We're just going left to right or right to left. It's the same thing. So if everything was exactly 50 ohms, then you would have infinite return loss, right? Everything would be transferred. The problem is everything changes. It changes with frequency, with your antenna. It depends. Raise your antenna one more foot up, and guess what? It changes its impedance. Put it closer to a wall, and it changes its impedance. Put it next to a piece of metal, and it changes. Change the frequency, and it changes. It's kind of a general thing. They move most often kind of irregularly. It's not just an even graph sometimes. It just depends. So nothing's locked down at 50, but we want to try to be as close as possible all the time.
Yeah, and you know that there was a good point made that the impedance of the antenna is not uniform, right?
Right.
So thinking through passive antenna system 75 ohm versus 50 ohm, definitely a consideration. It's not just a fixed solution or situation. There are quite a few variables at play across the system. A bunch of questions about testing cables. So, there are higher end, test and measurement systems, that we highlighted in that video. The point was made that some folks are using a less expensive solution, which would be something like the RF Explorer signal generator, where you can set up or sweep across a range of frequencies on the cable and then observe the result on the other end with something like the Pro Audio Edition spectrum analyzer or another lower cost spectrum analyzer. So there are some tools out there that allow you to run through. I don't know if you have anything to add to that, Don, in terms of like a process or
yeah. I mean, it realized the inexpensive signal generators are not real flat, not real even. I mean, they just have a much bigger tolerance. But yeah, you could go if you have an RF Explorer, if you have any kind of an analyzer, you need to get a sweep signal generator, and then you can do basically that test that we did, that we showed you with the Agilent. It won't be quite as accurate. Will it be good enough? It depends how bad your cable is. I mean, it's definitely better than trying to use a multimeter to do it, because a multimeter's telling you the DC response of that cable, and what you need to know is the AC response of that cable at very, very high frequencies. So that just won't work that way. So yeah, you can do it. I mean, there's, I believe there are specific cable analyzers. I don't know how expensive they are, but more than I spent for lunch for a whole week, I'll tell you. There are vector network analyzers. You can do it with that. There's a few other tools. They're all expensive though. It's just cheaper to buy new cables and go, unless you're using thousands of cables a year.
Yeah, some people from the integration world asking about installed cabling. Does it need to be replaced? I would say likely not in a fixed sort of secured install versus something like staging and rental, where it's just getting pulled up and deployed over and over again. That's where you see a lot of the wear. But have you ever run into that on an installed system?
Yeah, so I mean, again, if it's installed in a protected area, it's not in sunshine, it's not in a basement where they could get water in it. So we'll take those out of the equation. If it's just fixed and not moving, yeah, it should be fine for a very, very long time. That reminds me of something I didn't say for installers. So if you're pulling coax cable through walls or ceilings or whatever, and you're going to terminate it in a box, so that there's an RF connector, coming out of a wall box, you need to have 8 or 12 inches of slack in that line to be able to do that. What you sure don't want to do is grab that cable and scrunch it all up and put it back in that box.
Right.
That'll destroy it. So, I mean, that would be typical with electrical. If you're pulling, AC lines, you just fold that stuff up and put it back in the box. But you need to think about that a little bit on doing installs and kind of feed it back up through the box. You have to take up, like I said, you're going to have to take up 8 or 12 inches of slack. So just don't crush it, into a handful and then shove it in the box.
Mm-hmm. A few people wondering about, the age-old, how long a cable can I deploy before I need inline amplification? It's assuming, you've got a passive antenna. Any rules of thumb around that one? I know that's a question.
Well, you didn't watch last week's webinar about the link budget. So if you go back to that one, you can absolutely calculate it out. So there's a lot, depending on who you listen to, and I'm going to give you an answer that's different than other people. And you can take either answer or take them both and see how it works for you. So it's sort of the rule of thumb forever has been don't lose more than 5 or 6 dB between where you're receiving it and where it's going to, right? That's easy to calculate out. We saw it'll tell you the loss per foot or per meter for your cable. RG8X has a loss in the mid 500s of about 7 dB for 100 feet. Your antenna has a little bit of gain. So that would say that you could at least run that cable 100 feet. More than that, you start having extra loss, and then you would switch up to a bigger diameter cable, right? So the bigger diameter cables have a larger gauge wire in the center, and they just don't lose as much. So that's pretty straightforward. But generally, I'm pretty confident, generally speaking, that RG8X is good up to 100 feet. Can you stretch it to 150? Yeah, probably in a lot of cases. It always gets back to what your carrier to noise ratio is. You have to be able to measure the noise floor where you are, and then you have to be able to see how much stronger your signal is than that noise floor. And I like to keep it at least 20 dB more than that. Then you have a pretty stable system. Line amplifiers just by themselves, they amplify the signal level, but they amplify the noise. So you don't change the carrier to noise ratio, you change the voltage. You run the risk of overloading the input of your receivers or your distro or whatever. So we really only like present line amplifier, if it's just a line amplifier. Now there's some fancy line amplifiers that have some other qualities. Maybe they've got filtering or anyway, those might be a little different. I might reach for one of those sooner than just a plain line amp. But a line amp just increases the voltage. It doesn't change the carrier to noise ratio. So I only use those as a last resort. But going back to that link budget, it's just grab Jason's calculator there. The link's on the page, and plug in the numbers, and it's real easy. And you'll get a definite answer that's within a dB or two, and then you'll know if you're good or not. So if you look at that first before you go lay out a system, you'll know that you're taking the right stuff there, and you've got a really good chance that it's going to work the way you think it should.
Yeah, good call on the link budget. It definitely relates back to that and understanding, what your loss is, what your cable type is, how far the antenna is away from the transmit. I mean, it just goes on and on, right? To factor into that decision.
Everything's a plus and a minus, so you're just adding the pluses and subtracting the minuses and see what you got left.
Exactly. But specifically to cable, coax cable loss, I've been using a tool for years from Times Microwave Systems. That's at timesmicrowave.com/calculator, timesmicrowave.com/calculator. And it's just a really clean, really easy coax cable loss calculation. So if you're just trying to eyeball, loss per 100 feet or any run length, really, it'll calculate without getting into, a larger sort of link budget assessment. That's a really good kind of drive-by tool. People calling up or emailing, asking about, hey, I've got this much, RG8, or there's already, this other coax cable type that's in the infrastructure. That's a really handy tool to jump on. It's free to calculate your signal loss, including things like insertion loss, and there's a bunch of other specs in there that I don't think are really as important. But Yeah, check out timesmicrowave.com/calculator. I'll put the link in the blog post when we post this this webinar.
Yeah, I would also say, you know, you can also search. There are other link budget calculators that aren't as complete as Jason's. When you first look at Jason's, you go, wow, there's like 40 things I could put in here. I don't even know what all these things are. The answer is you don't really have to put them all in there. I mean, you're shaving fractions. His calculator is so good because it just considers lots of things. It considers the age of your coax, for example. You won't find that in a quickie link budget calculator. But a lot of those things you can just leave out. So it looks a little frightening the first time you use it, but seriously, just try it and plug in some numbers and you're going to see, again, what we're trying to see at the bottom, you know, is this a big number or a little number? You know, if I do this, did I improve or did I degrade my system? So that you know, because I'm guessing that an awful lot of people that are listening right now have never done a link budget. They just plugged everything in. Most of the time they have pretty good luck with wireless, and we'd like you to continue to have good luck with wireless. But it's just better to be able to know instead of to guess. And especially as it's getting harder and harder, you know, I think it's going to be harder 6 months from now or 12 months from now or 2 years from now to do wireless. There's more competition, so you're going to have to be a little smarter. But it's really not scary. Just plug it in, plug in some numbers, just play with it, and you'll see. You can leave an awful lot. You probably can leave, you know, 60% of all those calculations out. You know, you just that's why I did kind of the basic in the primer to doing that. You see, I didn't count everything because a lot of that stuff is just going to give you fractional, half a dB here and a dB and a half there, and well, okay, that does add up, but I'd rather know if that, you know, if I'm within 10, 20, 30 dB is pretty important. If I'm within a dB and a half or 2.5, you know, things change so fast anyway that it'll never lock down and you just have one number anyway. So I would look at that. But if it frightens you, a Google search will turn up another bunch of link budget calculators.
Mm-hmm. Let's see. Yeah, you know, some of the calculus around, you know, length of coax, and in, you know, particular situations where you've got a really long way to go, you start to think about RF over fiber as an alternative. So, you know, we had one question that just came in. Encountered a situation where we needed to run a pair of 200-foot RG8X to a second exterior location. LMR 400 wasn't convenient due to the size. Would fiber optic, you know, be a solution for something at that length?
Well,
I don't know.
It definitely gets. I mean, there's definitely
a crossover point, right?
Yeah, it's always a trade-off between cost and ease of use or installation costs. So there's, you know, equipment costs, there's the cost of the wire, but yeah, if you've got to run a 200 or 300 foot piece of LMR 400 or RG8, you know, through a ceiling or pull it through buildings and stuff, man, that's a tough job. That's very stiff, heavy, big wire. It's hard to do. And again, your bend radiuses have to be bigger and all that. And you really need to do it in one piece. You don't want to be slicing that stuff together because you lose at every splice. So it's difficult, you know, and if you have to pull it through a ceiling and you have to buy plenum rated, you know, fireproof wire, which is really expensive, you know, but if you're putting antennas in ceilings or you're pulling wire through ceilings in public buildings, that's code. You have to have that kind of wire, and it's enormously expensive. So at that point, you know, RF over fiber begins to look very attractive when you have to have, you know, when your wireless microphones are on the 6th floor, but your equipment's on the 1st floor. You know, how do you get it from here to there? And fiber's a really good way to do it. And fiber is so cheap. I mean, some people don't even roll it up. You know, I mean, it's just practically free compared to coax cable. Although the transponder and receiver for for RF over fiber are kind of expensive. So you're definitely going to leave those. So, but yeah, if you've got to do a racetrack or a golf course or something like that, I know we put those systems in a lot of, especially reality TV. They use them a lot. Survivor, where you got to pull, otherwise you'd have to pull cable through the jungle. I mean, that can't be fun. Fiber's really easy. 100 meters of fiber doesn't even weigh 1 pound. And you can hold it up with your finger. And like I said, it costs 20, 30 bucks. It's cheap. You just leave it. Well, we're ecologically sound, but I'm just saying we're not leaving trash all over the place, but I'm just saying it's so inexpensive that, in a big concert or something, when we used to have to run really heavy coax like that, I mean, you're looking at a $600-800 piece of wire. Yeah, we're gonna roll that up and take it back because it's expensive. So
cool. I guess maybe last question, Don. And there's been a couple variants of this. I hope I'm getting it right, but a lot of people are asking about what to keep your cables away from in terms of mains or video walls, or I mean just kind of sources of interference. What are some things to sort of think through in terms of placement of the cable?
yeah,
Say you're in just like a pretty typical like ballroom show or something where you've got like lights, minimal setup. Are there any things to kind of look out for there?
So, well, first of all, having 100% shielded cable helps a lot because obviously it's not going to pick up what's next to it. I mean, you'd have to check current code. I think NEC code says that that your coax cables need to be run 2 inches apart. And as I remember, there's some kind of residential spec. I can't remember what it's called, 570B or something. And I believe it says that those cables need to be 6 inches away from other wires. The best practice has always been, not only for coax, but if you're doing audio with mic cables and signal lines and stuff like that, if you're going to cross an AC cable with a signal cable, you should do it at right angles. It should cross at 90-degree angles. So you're making, an X with it. It will have the least interference onto the other cable when you do it that way. If you just sort of lay them side by side and cross them over, the effect, the ingress is much stronger to do it that way. So you should do it at 90-degree angles. I would also recommend, that's actually a good point, I would also recommend that with wiring inside a rack. We spent all these years learning to make beautiful looms so the cable was all laced up and nice to look at and tied together and all that. You don't want to do that with coax cables. Even an inch apart makes a big difference, right? Inverse square, at an inch, it's lost a lot more power than at half an inch or a quarter of an inch, right? So all the separation you can get, if you can get an inch or two between your cables, yeah, it looks like a rat's nest inside the rack, but it will actually work better. So you're picking up a fraction of performance right there by doing that. So I wouldn't lace these cables together unless I absolutely had to for some safety reason, some other reason. But if there's no other reason, they do work better apart from each other a little bit.
Right. Great. Well, we're right about at the end. Let me see if I can find one more here that we can touch on quickly. Filtering and, putting filters in on coax runs. A couple of good points in terms of like managing noise from, say, like an inline amplifier or even a fiber-based system where, you're going to have some kind of noise figure to compensate for. Just touch on the bandpass filtering subject just in general as a way to, be thinking about coax cable selection.
Yeah, so 2 things. I mean, filtering is the new miracle tool, frankly. It helps systems amazingly. But there's something I just Plain forgot to say. So again, these filters, bandpass filters that you would put in line, I believe are all passive. There might be some active ones, but they are passive, and they definitely have to be in 50 ohm cable, assuming they're made for 50 ohm. I'm sure there's television ones that are made for 75. They definitely have to be in the right impedance cable, because otherwise they shift value, and they won't filter where you expect them to filter, and the slopes may change. Lots of stuff can go sideways if it doesn't match up. But the filtering, filters in the line, of course, passive filters don't pass DC. If you have an active antenna, you have to put the power on the other side of the filter towards the antenna. What else about them? They have a tiny little bit of loss, but you pick up so much benefit from them in shielding, the outside world, keeping stuff that's out of band. Out of band interference is just something we never thought about years ago, and it turns out that things even that we can't pick up but that are close to us can be crushing us. So, LED walls would be one. Although new LED walls that are actually FCC approved are much better than what there was 5 or 6 years, 10 years ago. On the low end, walkie-talkies, those are mostly, in the 450 to 470 range. So they're right at the bottom of where you might be using wireless mics, and they're powerful, So when you get one of those close to your antenna or something, you don't want that signal bleeding into your antenna. It can overload the front end of your receiver.
Great. Well, Don, thanks so much. I appreciate everyone taking the time. Be sure to check out the blog for this recording, and go ahead and share that around, as well as the previous series. If you missed any of those are all there.
Yeah.
Don, anything to wrap up?
Yeah, I just wanted to say one other thing. I've been getting emails from folks all over the world. I spoke to email with somebody last week in Australia watching this. He's up at 4 o'clock in the morning to watch this. I'm really not that exciting, but I'm amazed. And
go to bed. Go to bed.
And the same way, if you're in Europe, it's already past happy hour there. So you guys are staying up late, and wow, thank you a lot. That's very gratifying that you could do that. All the rest of the guys in the States, well, wherever you are, you either just had lunch or you're just heading to it. So that's not a big a deal. But 4 in the morning, man, that guy gets a medal for that. So anyway, yep, I think we're all set there. And so thanks again.